Imagine you're an engineer in 1905, standing in a workshop in Winterthur, Switzerland. You've just realized something that should have changed the world immediately. You've figured out how to capture wasted energy, pure heat and velocity pouring out of an engine's exhaust, and use it to force more air back into the cylinders. More air means more power. It means smaller engines doing what only massive ones could do. It means efficiency you've never seen before. You draw up the patent, you file it, and then nothing happens. For 30 years, nothing happens. The world keeps building heavy, underpowered trucks that haul cargo at a crawl. Shipping companies keep paying fortunes in fuel. Aircraft keep losing power at altitude, and your solution sits in a filing cabinet while everyone ignores it. This is the story of Alfred Bucci and the turbocharger. A story about how brilliant ideas don't always change the world on schedule. Here's the thing most people don't realize about innovation. Timing isn't just about having the right idea. It's about having the right idea when the world can actually build it. Bucci had the idea too early. He was a century ahead of the materials science that would make it work. Alfred Bucci was born in 1879 in Winterthur, a Swiss industrial town that would become the engine room of European manufacturing. His father was an executive at Sulzer, one of the continent's largest engine producers. Young Bucci grew up around machines, around the constant pursuit of making them more powerful and more efficient. By 1903, he'd finished his engineering degree and started working in Belgium and England, far from Switzerland, gaining experience in different industrial systems. But something was gnawing at him. It was the waste. Every internal combustion engine burns fuel and produces explosion. That explosion pushes pistons down. But everything that comes out the exhaust pipe, the heat, the pressure, the velocity, that's energy simply pouring into the atmosphere. He couldn't stop thinking about it. What if you captured that? What if you used the energy that engines threw away to make them stronger? The concept was elegant in its simplicity. Take the hot exhaust gases, use them to spin a turbine. Mount that turbine on the same shaft as a compressor. The spinning turbine drives the compressor. The compressor forces more air into the engine. More air entering the cylinders means more oxygen available for combustion. More oxygen means you can burn more fuel in the same space, creating a more powerful explosion. The result: an engine that produces significantly more power without getting bigger or heavier. It should have been revolutionary. On November 16, 1905, the Imperial Patent Office of the German Reich issued patent number 204630 to Alfred Bucci. The official description called it a combustion machine consisting of a compressor, a piston engine, and a turbine in sequential arrangement. Simple words for an idea that was decades ahead of its time. But here's what Bucci didn't anticipate. The turbocharger he'd invented couldn't actually be built with the materials available in 1905. The problem was temperature. Inside a turbocharger turbine, exhaust gases can reach temperatures exceeding 1000 degrees Celsius. That's hotter than molten steel. In 1905, metallurgists didn't have alloys that could withstand those temperatures while also spinning at the speeds required, sometimes over 200,000 revolutions per minute. The bearings would fail. The materials would warp and crack. Every attempt to build Bucci's design fell apart. He knew the theory was sound, but theory and practice are separated by the entire landscape of materials science. Bucci returned to Switzerland in 1908 and joined Sulzer, where he had resources to experiment. In 1911, Sulzer opened an experimental turbocharger plant, specifically to test his designs. In 1915, he built his first prototype for a turbocharged diesel engine. It didn't work reliably. The materials couldn't handle the stress, so Bucci did what many brilliant engineers do. He kept going. He kept experimenting. He studied the problem from every angle. He wasn't inventing something new anymore. He was solving the constraint. If materials couldn't survive the temperatures, then engineering had to find new materials or new approaches to manage the heat. For a full decade after that first prototype, Bucci worked on variations, improvements, and workarounds. He experimented with different designs. He adjusted cooling systems. He tried new compounds. He was solving problems that didn't exist when the patent was filed. Problems that only emerged when someone actually tried to build the thing. Then, in 1925, something changed. Metallurgy had advanced. Manufacturing techniques had improved. Bearing technology had evolved. Suddenly, the constraints that had blocked the turbocharger for 2 decades began to yield. Bucci successfully installed turbocharged engines on 2 massive German passenger liners, the Preußen and the Hansgeist at Danzig. These weren't small experiments anymore. These were serious applications in serious ships, and the results were undeniable. The turbocharged diesel engines in those ships increased power output by more than 40%. 40%. In shipping, where fuel costs were astronomical, this wasn't just an improvement, it was transformative. 2 decades after his patent, Bucci had finally proven the concept worked. The Patent Office had issued the document in 1905. The technology became practical in 1925. 20 years of waiting. 20 years of being told it was impossible. 20 years of watching other engineers insist that heavy, underpowered engines were the only realistic option. But even after 1925, adoption was slow. Marine applications made sense. Large, slow-speed diesel engines could accommodate turbocharged systems more easily than fast-revving gasoline engines. Aircraft manufacturers started paying attention because turbochargers solved a critical problem. At high altitude, where air is thin, engines lose power dramatically. A turbocharger compresses the thin air back to sea-level density, allowing aircraft to maintain full power at altitudes where they'd normally be vulnerable. World War II accelerated this adoption. By the late 1930s, military aircraft were using turbocharged engines. The Boeing B-17 Flying Fortress had turbocharged engines. So did the consolidated B-24 Liberator and the Lockheed P-38 Lightning. These planes could fly higher and fight longer than their non-turbocharged competitors. It was a crucial advantage. But here's where the truck story really begins. In the 1930s, a Swiss company called Sora started producing heavy-duty trucks with optional turbocharging. Starting around 1931, their BXD and BZD engines were offered with turbocharged variants. These weren't military aircraft. They weren't ocean-going ships. They were the vehicles that hauled cargo across the landscape. Sora understood what Bucci had proven. In heavy trucking, where payload matters and fuel costs were astronomical, the turbocharger was a game-changer. Yet outside Switzerland, the technology moved glacially. American truck manufacturers didn't embrace turbocharging widely until after World War II. The innovation that could have transformed logistics in 1910 was still considered experimental in many parts of the world in 1945. This is what makes the timing so striking. The patent was brilliant. The inventor was persistent. The technology worked. But it still took 3 decades for the world to catch up. Think about what that meant for the industry and for society. For 30 years, trucks hauled cargo less efficiently than they could have. For 30 years, shipping companies paid premium fuel costs. For 30 years, transportation remained constrained by the weight and power limits of non-turbocharged engines. All that lost efficiency, all that lost time, all because the world didn't have the material science to make one brilliant idea actually work. The lesson here isn't that Bucci was a genius, though he was. It's that innovation isn't linear. It doesn't follow a straight line from idea to implementation. There are bottlenecks. There are constraints. Sometimes the bottlenecks is money. Sometimes it's social resistance, but often it's something almost invisible. The materials and tools available to turn theory into reality. Bucci's patent solved one problem, how to harness exhaust energy, but building that solution required solving dozens of other problems first. After World War II, turbocharging began its real expansion. The technology gradually moved into heavy trucks across Europe and North America. By the 1960s and 1970s, as emissions regulations tightened and fuel economy became critical, turbocharging became standard on commercial diesel engines. Today, according to some estimates, nearly every commercial engine is turbocharged. The efficiency that Bucci imagined, smaller engines producing more power more cleanly, became the standard solution for the entire transportation industry. But the timing was still 3 decades late. The revolutionary technology that could have transformed efficiency in 1910 didn't actually transform it until the 1940s and 1950s. Decades of inefficiency, decades of waste, decades of engines running at less than their potential. All because the material science wasn't ready. When you look at industrial history, this pattern repeats constantly. Edison didn't invent electric light first. He made a practical light bulb that could actually be manufactured and sold. The Bessemer process revolutionized steel, but it took years to scale. The transistor was invented in 1947, but personal computers didn't arrive until the 1970s. Every major innovation has this gap: the moment the idea becomes real, and the moment the world actually adopts it. Usually, the gap is about solving the constraints nobody anticipated. The turbocharger is just one example, but it's instructive. It tells us something important about how the world actually changes. Change doesn't come from ideas alone. Change comes from ideas meeting solved problems, available materials, manufacturing capability, and economic pressure all at the same time. Bucci had the idea, but the turbocharger, the thing that actually changed every truck on Earth, that only existed once material science caught up. Today, if you drive a modern car, there's a good chance its engine is turbocharged. If you ride in a truck or a train or a ship, same thing. The technology is everywhere. It's so universal that most people never think about it. They just notice that modern engines are smaller, more powerful, and more efficient. They don't realize they're experiencing the delayed revolution that Alfred Bucci imagined in 1905. The other remarkable thing is how Bucci's approach, using exhaust energy to power a compressor, remains the exact same principle today. Modern turbochargers are vastly more sophisticated. They use advanced metallurgy that can handle extreme temperatures. They have variable geometry systems that adjust the turbine vanes in real time. They have electronic controls and intercoolers and anti-lag systems. But the core principle, exhaust gases spinning a turbine to force air back into the engine, that's still Bucci's 1905 invention. A century of refinement hasn't changed the fundamental idea, only the materials and controls around it. What would have happened if materials science had advanced just 10 years earlier? If the metals were available in 1915 instead of 1925, would trucks have been turbocharged by 1925 instead of 1935? Would the entire logistics industry have been transformed earlier? We can't know for certain. But what we do know is that innovation and timing are entangled in ways we rarely acknowledge. Good ideas don't automatically change the world. They change the world once the world is ready to build them. The bigger pattern in this story is humbling. We celebrate inventors as if they're visionaries who single-handedly transform civilization. And some are, but most innovations are solved constraints. Brilliant ideas waiting for materials science, manufacturing techniques, or economic pressure to align. Bucci was a brilliant engineer, but he was also a man fighting materials that wouldn't cooperate with his vision. He was fighting the timeline of metallurgical progress. And for 30 years he lost that fight. But he kept working, and eventually, the world caught up. The materials arrived, the manufacturing techniques evolved, and suddenly, the turbocharger became the obvious solution to a problem everyone had been living with. Power delivery in trucks, efficiency in engines, the ability to produce more output from less displacement. All of that became possible once the constraints were solved. So here's what I find remarkable about the turbocharger story. It's not about a sudden breakthrough moment. It's about persistence through a constraint nobody could have predicted. It's about an inventor who believed in an idea so deeply that he spent a decade refining a design that couldn't possibly work with the tools available to him. And it's about the moment when the world's materials science finally caught up to his ambition. If you're interested in how innovation actually happens, not the way it's told in popular history, but the way it really unfolds, the turbocharger is the perfect case study. It shows you that the gap between idea and implementation isn't usually time. It's resources, materials, and willingness to solve the problems in between. Which diesel innovation do you think had the biggest impact on the world? The turbocharger was just one piece of the story. There were advances in fuel injection, combustion chamber design, and manufacturing processes that all contributed. Leave your thoughts in the comments. I'm curious which moment you think was most transformative. If you enjoyed learning about how real innovation works, consider subscribing for more deep dives into the stories behind the technologies that shaped our world.